Anybody else comes in late, I'll just let them in as we go. Today is going to start talking about the LG washer. I don't know if you've been following the videos I've been posting online, but a lot of videos on many different mechanically controlled washers with timers. And I started off that way with the students to not only get an understanding of the diagram, but also to understand timer sequence charts, what a cycle is. It's important to remember that it's good to know these schematics, but in servicing appliances, you don't use schematics every day. You know, there's only certain situations where you're going to actually pull a schematic out and to make some tests. You're either going to go through diagnostic mode and it has an error code or stuff like that, but schematics are good if you understand the components of the machine and the purpose of what those components are. Why did they put this sensor here? Why did they put this thermal fuse there? Knowing that information is just as important as being able to read and understand a schematic. The schematic is that if you say, hey, I think that this door switch is not working, or I think this pump is not working, how is it getting power? That's where we need to go into these schematics and try to find out, okay, am I getting power to this pump when it's supposed to be pumping or circulating or something like that. So today is going to be one of a multi-part series that I'll just do for members, and I'll put in the members section of the video. Is I'm going to go over the schematics, but I'm also going to add in troubleshooting. In my public videos there'll be a lot more troubleshooting as well, but I'm working right now on building online learning. The sealed system one is up as a beta. I'm going to actually move it over to another site, but I'm working on the washer and dryer one too, where I'm going to go through the whole entire appliance. So all this home study stuff will be soon posted up there. But anyways, let's get into the schematic here, and let's just break down some of the parts first, and then we'll talk about testing and how some of these parts operate that are just not you know, plain like a drain pump. You know, a drain pump's a drain pump. It's not that difficult. But why do they have so many different things that they have here? Let's start off just going left to right on the schematic, identifying the components and what they are and why they're here. So here we have a lamp, but what is this symbol? Does anybody know what that type of lamp is? By the symbol? It's a diode, or you might also know them as something called LEDs. LEDs can take 120 volts and they can operate normally, but you cannot own those bulbs out. That's just a lamp if the customer opens up the door at night and they want to see their clothes inside. But if this light's not working, this is an LED light. You cannot use an ohm meter to test to see if the light's functional. The only way to test out an LED lamp is to check power, and you just go from pin 1 and pin 3 on the board to see if you got voltage going to the bulb. If you don't have power, the problem's at the board. If you do have power, the problem's at the bulb. If you guys have any questions, just don't hesitate either to type it into the comment or to ask. Okay, so we have two thermistors here. We have a wash thermistor and an AG thermistor. I'm not going to give you guys the answer, but does anybody know what the AG is for? I will tell you is that we have an AG heater over here, and we have an AG sensor over here. So what is that thermistor for? What is the AG sensor, and what is the AG heater? Why do they have those three parts? That isn't normal in a regular washing machine. Wow, you guys really don't know. that is the steam sensor inside the washer and the heating element to produce steam. Let's go to, I'm going to bring up the manual. Let me see if we can see the manual here. I have to share the window. Hold on a second. Okay, I'm in the manual now, and I want to go to the heaters, which was page 42 in the book, right here. So here we have, notice they call it a steam generator heater here, where in the wiring diagram it's called an AG heater, and I'll go back and forth between the two. Just want to explain this out. So the wash heater is to heat the water in the clothes. When do we use the wash heater? Does anybody know what cycle we use the wash heater in? We use it in many different cycles. We use it for sani temp. We use it to help reduce stains in whites and clothes like that. So the wash heater is used to heat the water. Notice, and I'll zoom in a little bit on it, notice that the heaters both have fuses internal into the actual heater. You can see they drew it over here and then they just flipped it so the word fuse is backwards. I've noticed a few mistakes here on the on their technical diagrams. So this heater's used to create steam, but where are they located? Let's take a look for a second now. First, I want to point out another thing. The wash heater is designed to raise the wash water temperature to desired temperature during wash cycles. The steam generator, and this is their English, the steam generator heater is designed to make the water to the steam during steam cycles. What they meant there is that it's designed to turn the water into steam, and then we add steam in it. Steam is used for people that might have allergies or bacteria, and it's also used to help reduce the mold during the tub cleaning cycles. So here you see a heating element here with a sensor on the side, and now we got a heating element here. We're not seeing the sensor here. I'll show that to you in a minute. But this is on the bottom of the tub for the washing machine. This is where your detergent dispenser is. This is not located on the tub, and I'll show you some more images of that. So here you can see a little bit more clearer picture. This is the heating element with a thermistor. This thermistor on most models would be attached right here to the heater bracket, but in this case it's a sensor that goes inside the tub here. And this is our steam generator thermistor. So this is how the control board knows the temperature. So let me bring up a picture here, and I'm trying to figure out how I can get it to show the whole entire screen. That might work better. Okay, so here is the actual steam generator assembly. We have a couple of things here. This is our sensor, our thermistor. We have two other sensors, one here and one here. Those are our water level sensors, and I'll show you to them on the schematic. First, I'm just pointing out the components to you. And we have a heater. You can't see it here. I'll show you in another picture that's on the side of the unit. And here you can see the heating element with the ground wire attached to the center. So this is the heat that creates the steam inside the steam generator module. So let's go back to the schematic for a second. Now if you're looking at the schematic, we have our AG thermistor. Okay, that is what's telling the board the temperature of the steam. That is controlling the heating element like a thermostat would be. That's telling the board turn the heater on and off, which is this heater right here on the steam generator. Now this sensor here, you see it has L, S, and ground. So if we go here and we go back to our steamer here, we have two sensors here and one here, and they both go to ground. So what happens is one of them, which is probably this one here, is the low water level sensor. So if we run out of water and we don't have enough water coming back in, the sensor will alert the board and it will make sure the heater don't come on, because if the heater comes on with no water, this plastic housing will just totally melt down. This other sensor here in the upper left hand side is the high water level sensor, like a water level switch, so that the machine doesn't overfill with water. So we have a low level and a high level sensor and a heating element in here, and then the steam is generated in here and pushed out through the hose. Now this is connected up by the dispenser, so if we look, there's one more AG on that schematic. Let's see at this diagram. I found a fuse, I have the sensor, and I have a thermistor here, but there's one more part that I didn't point out, and that is the AG water valve. That the thermistor has its own water valve, which is part of the water valve assembly, that will refill the sensor with water so that we can have steam. So if we were to test these sensors out, we have our wash thermistor and our AG thermistor, but if we look, the wash thermistor jumps over here and jumps to pin 5. That is our common terminal. Most of these, yes, give me 1 second, I'll try to enlarge the schematic. So if we look here, the wash thermistor and the AG, I've been searching everywhere for days trying to figure out what AG stands for. I don't know what the acronym is, but it is the steamer. But if we were looking at, if you notice, this one wire coming off of the wash thermistor jumps off of this pin 1 and goes to pin 5 on the board. If I wanted to ohm out these heaters, or these thermistors, I'm sorry, we're going to check from 5 to 6, or we're going to check from 5 to 4. They're both using this common terminal. Now this is most likely low voltage. It's probably going to be like 12 volts DC, and that's what the board will use to sense the temperature. Let's go ahead and go to the schematic of that board. 1 second for the thermistor test here. So here for the wash thermistor, the thermistor is a resistor that changes resistance value based on temperature. And if you see, we have 39,500 ohms, and this is 2,800 ohms. That's what K means, kilo ohms. Tolerance plus or minus 5% means it could be 5% higher or lower. So if it's 5% of 200 would be like 50, it could be 50 ohms higher or lower. But if you look, our temperature is 86 degrees, but our resistance is only 40,000 ohms. But as it gets hotter, now we went to 221 degrees, our resistance went lower. That is called NTC, negative temperature coefficient, and that is when the resistance goes down as the temperature goes up. You have positive temperature coefficient, which is that both the temperature and the resistance go up and down together. Here you see the steam generator. It's pretty much the same resistance values. If you look at 2,800 at 221 degrees, this one is the same, so that they're technically interchangeable, but notice that this one has a lot larger scale, up to 356 degrees. Now water boils at 212, which is down here, but when you're making steam and steam is trapped under pressure, the temperature of that steam could get way hotter, so that's why our scale goes way up. Look at, only at 400 ohms, we're at almost 360 degrees. So that is the sensors to sense the temperature of the dispenser, as well as the steam generator here. So here you can see a close-up of the the heater assembly and the generator assembly here. Here's a schematic. So they're saying it's 5 volts DC going to the low and high sensors. So if you had a board telling you, hey, there's no water in the steamer, and you say, that's not right, I have water in my steamer. Well, what you'd want to do is you want to check voltage going to your sensors. If you had voltage going to your sensors, that is telling you your board is sending the power to those sensors and it's not reading the sensors. So the first thing you want to do is you want to make sure that you're getting power. And if you look, here's the ground on one side. If we're going to look, this is the common terminal, and then these two are the positive coming off. So pin 4 and pin 2 is positive and pin 1 is ground. So if you're going to check these, you're going to check pin 1 to 4 and pin 2 to 4, depending on whether you're doing the low water sensor or the overfill sensor. Now the sensors themselves cannot really be ohmed out. They're just like almost like a piece of metal. So you can check them, but they have to be checked for ground, and you'll have a very high resistance. I don't know if they actually tell you how to check them. I don't think they do. So here's a sample of the water level sensors. We can take a look at them there. Let me just look real quick. Just that this model had a few extra things that I didn't read about before I started the class. Okay, so here is your low and high water level sensors. So from one pin to the other pin, when the water comes up and actually goes across those two pins, that low voltage, that DC volts that is being sent to it, comes through the water and comes up the other side, the sensor. So then here, if the water rises up now and touches this one, it still uses the same common sensor, and then this one will send voltage there, telling the machine, okay, we have enough water, stop filling, to prevent it from overfilling. Let me see here, steam generator supply assembly. There's not much there. You guys could read that. I'm not going to read word for word off of the book for you. So here's just a picture of the drum lamp when there's power on. Let's see how much voltage it has. I thought it was 120. Could be wrong. No, it is low voltage. Look here. This one is low voltage. It's 16 volts. Now, which one is positive and negative? Well, if you look at this 16.5, this is most likely the power side. I don't know. I think it's the ground side. This is a transistor or a triac, which has 3 pins on it, and so when voltage is applied, it's like a switch and it closes, almost like an electronic relay, sends power to the light and out. So in order to check this, we're actually going to be looking for about between 15 and 20 volts off your pin 1 and 3, and if you have that voltage and the light don't work, the light's bad. Let's go back to the schematic. Now here we're looking at the motor assembly. I'm going to move this out just a little bit. So here we're looking at the motor assembly. If you look at this motor, this is one of those big round motors that look like ceiling fans, and they have 3 windings inside of it. So in order to check this motor out, you're going to check with continuity pin 1 to 2, pin 2 to 3, and pin 1 to 3. So if you did that from the board, you could ohm out the motor here. 1 to 2, 1 to 3, and 2 to 3. I think that's how you would check it. And you would get all 3 resistance readings the same on this type of motor. I've honestly never seen one of these motor windings ever fail. I've seen the motor not work, but it's usually due to the thermistor or the Hall sensor, which is what this piece is here. It is part of the motor on this model. On some washers, the Hall sensor is separate and can be removed and installed. This piece here is the sensor for the motor. It tells the board the speed at which the motor goes and the direction that the motor's turning. So when we check that, that's got to be done through diagnostics. And let's take a look at that in the book. Let me just search here. I don't know what they called it in the schematic, so we'll just here we go. Let's take a look at this real quick. Rotate clockwise. There we go. So if we're looking at the motor, so here is how to check that sensor. If we look here, it's on this white, red, blue, and gray wires on this one plug right here. From pin 1 to pin 2 and pin 1 to pin 3, we have 8 to 12,000 ohms. So pin 1 and 2 and 2 to 3. So if we look at it, 1 is going to this plus sign. I really don't know what the actual symbols are on here, but to 2 would be HB and to 3 would be HA. So those are the sensors that are telling the board the way it works, the motor speed and the direction. Like on a lawnmower, like with a spark plug, there's a flywheel that spins around and has a magnet, and every time that magnet passes a coil of wire, the spark plug sparks. That's the principle at which these things work. They have like a little magnet, and every time the magnet passes a coil of wire, that coil of wire gets like a little magnetic field for a split second, and it tells the board that the motor has been rotating, and how fast it pulses is how fast the motor is rotating. So we go back to testing that in the diagram here. We have 10 to 15 volts going in, and we have a pulsating DC volts here of 10 volts on pin 2 and pin 3 to 4. So 2 to 4 and 3 to 4 on these plugs right here, we're going to get a pulsing from the board. So you're not actually checking the sensor at that time. You can check the resistance value, but you also want to check the voltages coming off the board, because if the board is telling you the motor has a problem, then you don't know whether it's the board not sending the signal to the sensor or the sensor is not picking up the signal of the motor. I can give you a quick example. The VMW Whirlpool washer, the top load washer. A Maytag version of that was made, and it's not the same as this front load, but I just want to give you a scenario of something that happened. The motor wasn't running, so the technician thought it was the motor, and he changed the motor, and then he changed the board, and he kept getting errors that it wasn't sensing the unit. Now, the sensor in the Whirlpool VMW is not part of the motor. If you look at this dotted line going all around here, on this machine, if you were to change the motor, which is the windings, the sensor comes with it. But one second, I'm trying to pull up a part here. Okay, here we go. So if we look at this here, and I know it's not the same things, but I just want to give you different scenarios and how one machine it's this problem, one machine it's another problem. So on this is the shifter motor for spin and agitate on a Whirlpool VMW washer. But I wanted to show you was the upside down version of it. And if we look at it close up right here, these two pieces right here, when you mount this in the washer, part of it's not really a transmission, but the transmission has a big black circular dome inside of it, and it spins right between these two. This is almost like a pickup, like when you go into a clothing store and it beeps as you walk in. This here sends an infrared signal between these two as a beam, and that's how it picks up the speed. So going back to why am I talking about this washer? Well, the complaint of that VMW washer is that the motor wasn't working, but it wasn't able to see the motor running. And so I told the guy, well, you changed the motor and you changed the board, but on that particular washer, the speed sensor is attached to the motor shifter. I told him change the motor shifter. Guess what? That didn't fix my problem. The motor shifter is how that unit is sensed for the cycle, but one second, I'm trying to bring another window back up. But I'm sorry, I lost you guys as far as the screen. Let me there we go. I'm sorry. So I said your motor speed is controlled by that shifter. Change the shifter. So he went and changed the shifter. Guess what? On this particular model, the shifter didn't fix the problem. So most likely you'll think that, oh, my problem must be the board then, but he changed the board. Well, the sensor on his was in the shifter and we changed that. It turned out that unit has a capacitor on the motor, and their capacitors are exploding and leaking fluid. And when that happened, the capacitor wasn't allowing the motor to run properly. So a lot of people thought, well, if the sensor was not being read by the unit, that's why the motor's not running, because it can't read the motor. In this case, the capacitor was preventing the motor from running. The sensor couldn't see the motor run. So this sensor is mounted on there. Make sure you know where the sensor is on the brand machine you're working on. In this case, it's located right on the motor. Let me see something real quick. I'm trying to find you guys a picture. So if we look at this picture here, I'm going to bring it over in a second. So if you look at this picture here, great. If you look at this picture here, this is the motor, and this right here is the actual motor windings. There's 3 holes here, and those 3 holes are connected to these windings here. So even though there's a bunch of them, there's only a set of 3, and they're connected every third one. Now this here, this piece in the black, is the actual sensor that I'm talking about on that motor. So this is the sensor. On some of them, this can be unclipped and replaced without replacing the motor, but a lot of times it comes with it. Make sure that when you order your motor, if you need the sensor, that the sensor comes with it. Look at the parts breakdown and identify that. Here is, as a matter of fact, I just found, here's a picture of just the sensor. If you look here, this is what that sensor looks like. And if you look right here and right here, you can see it's dark up into this point. These 2 points here are what is picking up the actual rotation of the motor and being fed through here. So the pickup is all part of this. The rest of this on this end is just support for that into the motor. So let's go on to the pressure switch. The pressure switch is a pressure sensor, not a switch. You cannot check that pressure switch with an ohm meter. You have to do that through diagnostics or using a meter that has the capability of measuring frequency. Now if we look here, I have to rotate clockwise twice now. Well, actually 3 times. So here the unit can only be checked to measuring frequency, and when the unit is empty, this one here is going to probably read about 24,600 kilohertz or 24.6 kilohertz. So you will not necessarily have a meter that will read frequency. So in order to do it, let's just go to where it's actually here in the sensor. In the diagnostics, let me see something. Well, they are telling you here pin 1 and 3 is going to read between 22 and 23 ohms. I was always told that you could never ohm out these pressure switches. He's testing the outer 2 pins. I know that picture's blurry, but you have that in your manual. He's checking the outer 2 pins for continuity, but really the best way to check that would be to run through diagnostics and troubleshooting. Let me see something. if I can get to the page where we're going to do. Well, it didn't take me to where I wanted. I want to get into the diagnostics, but to get into diagnostics, you're going to just press, let me see if I can find the display here. To get into diagnostics, you're going to just press these two center buttons here, okay? That is soil level, and I forgot what the other, spin speed. When you press and hold those down, let me see, maybe I'm looking for diagnostics. When you press and hold those down, that will get you into, you don't have diagnostics. Give me 1 second. Troubleshooting, test mode they call it, page 18. How to check water level, here we go, 7.3. How to check the water level frequency. So here, when you're going to go into this unit, you're going to check spin speed and soil level. You're going to press those two at the same time, and while you're pressing them, you're going to press the power button. When you do that, you're going to hear the buzzer or the beeper indicate that you're into the diagnostics, and all the LEDs should light up. Like if you see here, here's an example. Every light that display has will light up, and that's the first test you're making, is to see if any of the LEDs are not working. Like if someone says, oh, the spin light's not coming on or something like that. So here, if you press the start pause button, you'll advance yourself through these different steps. And if you look down here, you're going to get to water level frequency. So when you get into the 11th time, the circulation pump comes on, but our water level frequency is going to show between 25 and 65. Well, why are they showing these different levels? It depends on how much water is inside the machine. Here, if we're checking just the water level sensor for steam, we're going between 0 and 255 frequency. Okay? So how to check the water level frequency? Press the wash, rinse, and delay wash button simultaneously. The digits should indicate the water level frequency of 24.1 kilohertz. So instead of going through diagnostics, I guess they want you just to press these two buttons, and by doing that, it should say 24.1. Note, they don't say it in here. This is only when the machine is empty and does not have any water inside the washing machine. Now, if you notice, it's 241 kilohertz, but as the water goes in, the frequency should actually drop. It does not go up. So let's see here. Let's go back to the schematic. So that is the pressure sensor. The best way I've always been to test it is through diagnostics. And even though they do give you ohms reading on there, I've never was successful in ohming out many of those sensors. Those sensors are better tested going through the diagnostics or the troubleshooting that they have inside. Here, if we look, we have our water valves. We have 5 different water valves. We got the hot, we got the bleach, main wash, pre-wash, and AG valve. So what happens that when we have different compartments in our dispenser, certain areas we only want cold water to be in, certain areas we want hot water to be in. And so that's why we have so many valves. If you looked at the dispenser itself, you might see 4 or 5 valves or hoses coming off the valve going to the dispenser. And that's so that when we energize one valve, like the bleach one, it's only putting water in the compartment holding the bleach and dispensing the bleach. So all these can be checked out by voltage, and if you wanted, you go through the diagnostics here, and you could actually, energize each one of these components through the diagnostics. I have to go through the test here to find out which one the test it is. I'm not going to waste time on that, but going through diagnostics, you can energize each one of these valves and see if the bleach valve is working, the AG valve is working, and just put your voltmeter on there. If other valves are working, know that the problem's not water coming in, so it's either the board not sending power to the valve or the valve not sending power out. Now, if we look here, we got two pumps. We have a drain pump and a circulation pump. Not all machines have circulation pumps. This one here, they're both connected to the same housing. Let me see something. I did have something that I created. I could email it out to you guys if you want. It's a paper that goes through each one of these components and has pictures and says this is how you test this one part. So here I just want to show you real quick a picture. I'm going to bring it over. This is an LG washer pump, but if you look, it's got two motors on it. It's got, let me see if I can, I don't want it rotating. So we got one motor here on this side, and we got another motor on this side. So one housing, but depending on which pump that we're energizing, we could either be recirculating the water or we could be draining the water. So this here is the filter that you can unscrew from the front. This hose goes to the tank on the bottom. Can you guys tell me which one is the wash and which one is the drain pump by looking at this picture? Or just take a guess?
I would assume the one on the left is the drain and the one on the right is the wash, just due to the sizes of, if you want water coming in, I think you want that more metered. When you want to expel it, will quickly do the...
Very good answer. You are correct. The smaller opening here is going to go back up to the dispenser because it may want to dispense fabric softener or whatever, and it's just going to use the existing water inside the tank. And what happens is, you know, when you're washing with a front load washer, once it fills with water, the clothes are just lifted up by the basket and they splash down into the bottom of the tub where the water is. And that's good because it, you know, splashes the water, forces water through the clothes to pull the dirt out. But sometimes people put so many clothes in there they still don't wash that well. So by being able to recirculate the water through that circulation pump, that water gets pumped back up to the top of the machine and sprays down onto the clothes almost like a shower. And that there helps get the dirt out of the clothes. Now with the drain, we have a larger opening because when we want to pump out, we want to get that water out as fast as possible. So yeah, we're going to use a larger diameter opening on there, and it was a very good prognosis there. So let's look at this door lock assembly. I have a close-up view so we can understand. This door lock is a little confusing if you never actually worked on one. Let me see here. That is not the same machine. I think I need to do it in the book. I'm sorry. Give me 1 second to go to the book. Okay, so let's take a look at this door switch assembly, and then I'll go to the stuff here on the left in a second. So if you look, we got 4 terminals here. Alright, let's start off by looking here. You know what, let me bring that into my software so I can draw on it, because I want to make a few notes here. There we go. So if we take a look here, we got volts AC, right? And it's really weird because the volts AC here goes to the board, but over here it says 12 volts DC. This here is not DC volts. This is AC volts at this point. And here it says AC common terminal. So if we look, that AC voltage comes in and goes to red and ends at this switch. Now, what we want to do is we want to energize this solenoid here to lock and unlock the door. And the arrows are telling you, well, if I turn the solenoid on, I pulse it one time, it locks. If I pulse it another time, it unlocks. And that's what these relays are doing, and I'll show you that in a minute. But they energize this solenoid with just like a pulse of voltage, and the door is supposed to lock. So what happens is if the door locks, it completes a circuit here to this terminal ground, and by doing so, the board knows that the door is successfully locked and the switch closed. Let me just clear this for a second. So we have these PTCs, and I just mentioned a little bit about the PTC when I talked about the sensors. PTCs are also used as a control. Your refrigerator compressor, just a basic refrigerator relay and overload, used to use a relay like this where it had a switch and a coil, and the switch would disconnect the start winding. Well, they went away from the actual magnetic coil and they went to something called a PTC, which positive temperature coefficient means when the temperature goes up, and I'm just going to put temperature, the resistance also goes up. When the temperature goes down, the resistance also goes down. So what causes this thing for the temperature to go up or down is when current is flowing through this circuit here, it's going to heat up these PTCs. By heating up the PTCs, it's going to raise the resistance. So if a slight voltage was to accidentally pulse there and unlock the door when the machine's running, so a small current is passed through here to keep the PTCs hot so that the solenoid does not unlock the door accidentally. And that's what the PTCs are for. So in the book here, it tells you how to check them. If you look here, after the system turns on, the PTC heating starts up through terminals 2 through 4s, authorizing power on. So when that happens, the PTC heating starts up, and before the solenoid operation is driven, forces the system to the off position through CAM. So their English on this writing is horrible. Remember, this LG is Korean made, and then it's translated to English. So whoever's translating it is probably Korean and still don't have a good English diction. So what happens, the CAM is when I pulse a solenoid once or pulse a solenoid twice, I don't have a picture of it, but it shifts into the lock position, and then it shifts again into the unlock position. And the solenoid's just moving the same way, backwards and forwards. But it's the CAM that shifts it. So that's what they're talking about here, where they're saying the CAM is the one that forces it in the off position. So what happens now, you close the door, that authorizes one impulse through terminal 3, 4, the PTC and the solenoid. So 3, 4 are these two here. Okay? So that sends a pulse through there. The door lock is detected when switches in terminals 4 and 5 are closed. So when 4 and 5 are closed here, then that tells the machine that the door has been locked. Okay? Then the CAM rotation will forcibly clear the off position connection. So inside this little CAM, it's just a little plastic piece that when the solenoid moves, there's a lever that moves that CAM back and forth. Upon the third authorization of the impulse, the position CAM goes back to the door open position. So in other words, it energizes a second time. It energizes once, the machine runs for a few seconds. It energizes again, then it energizes the third time. Normal operation of PTC heating from 1.5 to 5 seconds. Defects from the development process. I don't know what they're saying here, but they're saying is that PTC is going to heat up within a few seconds, and that'll keep the unit from operating accidentally. So here's what the door lock mechanism looks like. These are the pins that they're talking about when you're testing, pins 3, 4, and 5. And here are the readings you should get when you're testing that lock. From pin 2 to 4 is 700 to 1500 ohms. That's 2 here and 4 here. If we look at the diagram 2 and 4, to here goes in through this PTC and it goes to right here, and then it goes to terminal 4. So that PTC is heated up right now. Oops. That should read from 700 to 1500 ohms, and again, that's dependent on whether it's hot or not. And since it's PTC, 1500 will be an indication that the power is being sent to that board. So if you wanted to check voltage, you could check voltage to it. If you want, you could check resistance, and when it's cold, it should be 700 to 1500. Pin 3 to 4, which are these two pins, from 60 to 90 ohms, and if we look at the diagram, 3 to 4 is through this PTC and the solenoid, and it goes here and goes back out. So that is this solenoid and this PTC. Oop, I keep minimizing, think I'm in a different screen. And then 4 to 5 is infinity no matter what. And 2 to 4 is 120 volts AC. And if we look between 2 and follow that circuit around, and 4, we should have 120 volts AC. Wait a minute. I don't know what this is. Input voltage of 120. So these two wires here, that's what that is. Okay, I just realized that was 120 here. I don't know why they got it connected to a DC circuit on the board. That's probably just neutral on the board. It's just a bad drawing. If we go back to the diagram, if you look, this circuit is not the same as that they have here, but this here, when you see that symbol, that is most likely power coming in from the wall. That is voltage AC coming in. So if we look at the diagram here, volts AC would be here and here. When they're doing the test, they're saying between 4 and 5 you can check ground or check for voltage. Between, I'm sorry, 2 and 4. So if we go back here, 2 is here and 4 is here. 4 is coming in. Well, where is this coming out? Well, 4 will be to here, and then it goes to here, which is this PTC, I guess is what they're checking voltage to. So the voltage being, I had to figure this out for myself. So the 120 volts between pin 2 and 4, I think that they're telling you, is that 2 and 4, right? 2 and 4 is checking the 120 volts to this PTC, so this one gets 120. Alright, so going back to this here, 120 volts AC input. So if your door is not locking and you're getting these resistance values and you're getting this voltage, the only thing you need to check is the voltage going to the solenoid, okay? And that solenoid is running off of 12 volts. It comes in through this relay, or it comes in through the other relay, okay, pin 1 or pin 2, and apparently because it's 12 volts, the polarity that they're running through it, let me see if I can find the circuit for that. I'm just looking at this circuit for the first time. This is a new switch. The other ones I'm used to have multi-switches inside. They didn't have this ground, so this is actually new to me, guys. So if we look at this, let's take a look at it. We got volts DC here. In order to have DC volts, you got to have both a positive and a negative path, right? So if we come in here, I'm telling you, I don't know where the other side of that load is. We go through this relay, and this relay is going to feed pin 2. I'm going to go through the PTC through this solenoid, and it's got to go through the other PTC, I'd assume. through these relays. But there's something wrong with this diagram, guys. I don't know how we're getting the other side of the 12 volts DC to that lock. Let me look at the instruction one more time. I apologize. I'm thinking there's something wrong with their diagram, because they're telling me 120 between 2 and 4, but I have 12 volts DC, and I don't know where that 12 volts DC is applied to that lock mechanism. It's got to be to the solenoid, but it's not. That's that impulse voltage, but their diagram is not accurate, because here you have 12 volts, but where's the other side of the 12 volts? I see it, I think. No, it's still, they still have a mistake here, because this here, this 12 volts is the 12 volts positive. I'll show you here. This is our 12 volts positive, and then this has got to be our negative, our ground, or vice versa. So I do not see how they're changing. They're not drawing this correctly, because you can't go through this solenoid. Let's just say I go through here. I go through the relay. I'm gonna have to find a better diagram and correct this lecture here. Goes to this PTC and to the solenoid, but when you come back through this other side of the circuit, it takes me right back to where I started, and it shouldn't. You should have a positive and a negative, and I don't have both a positive and negative. I only have one terminal. There is something wrong with the schematic. So I'll do a follow-up on this in the next lecture, and I'll record it in case you can't make it. But there is, I'm telling you, there is something wrong with the schematic. I found other problems with schematics before, but this one here, the voltages applied to this switch is not accurate. Let me just see 1 second. I had a different diagram here. This one here is shown differently, but it's all 120. So that one's not going to be it. I'll have to figure that out. I apologize, and I got stumped. I don't know what's wrong with that circuit, because they're showing AC and DC on there, and they have the wires confused. I think I corrected it in my drawing. Again, I can send that out to you, how to test these components out. Let's go to the actual motor circuit, not the motor. The noise filter is something else I wanted to point out. This is the noise filter. Most noise filters have an input and an output, and I saw something that, let's see if I have that picture. I opened it up. Maybe it's in the book. Here's the noise filter. That's not the one I want. I want a picture of it. Okay, so here's a picture of the noise filter. I know it's not the best quality image, but look, this one has 3 plugs on it. This is what was also something different on these machines, is you got 1, 2, 3 plugs on it. On most noise filters, there's only 2, power coming in and power coming out. If we look at the schematic here, not this one, this one here, the power comes in here on the white plug. So if we look here on the white plug, this is input power, so there's 120 volts here all the time. And what we have is some capacitors and some coils of wire which take out the input frequency or the output frequency of the washer and prevent it from going through the whole machine. Now, if we look at the schematic on this unit, the schematic shows this is what's going into the board. So if the washer's not working, we check power here, white and black. Going out, we're going to check brown and yellow. Green, I think, is the middle for ground. And that is feeding the board here and here on 2 different plugs. And it's black and I guess it's a blue wire. That's green and yellow to ground. I guess it's blue here. So power comes in, power goes out the noise filter, feeds the main board. right here we have this other one. So it's PLC modem. PLC modem is like for Wi-Fi. So if your machine had Wi-Fi on it, this would plug into a separate modem. I don't know if this is similar to like GE now, where GE has a Ethernet plug where you could plug in the Smart HQ and you could diagnose the washer through the Smart HQ. This might be because LG and GE are basically the same company. LG has put, I think, one of those sensors in their dispenser area. If you haven't seen them, they got something called Smart HQ, and you can plug into the washer and you could check every one of these sensors, energize any one of these components. Instead of using the machine's diagnostics, you can use the Smart HQ diagnostics, and it could troubleshoot the machine out for you. It is quite expensive though. If those of you guys haven't really looked into it, if you don't do a lot of GE product, it's not worth it. I had 20 plus technicians, and when I first started with GE, I bought a Smart HQ for all of them. It was $10,000 for a year to have that many devices for my employees, and I asked them to give me a report, and there was only like a handful of guys that were actually using it. So if you're not going to use it, it's not worth it. But it's probably going to cost you between $50 and $100 a month to have that device. So if you do a lot of GE or do GE under warranty, and it'll work for COD also, I recommend you get the Smart HQ. If not, then it isn't worth the extra money. Problem is all these manufacturers now are starting to come up with their own diagnostic tools, like Samsung had Haas and all these others. We can troubleshoot these machines without it. We just got to know how to use the diagnostics and know what all these parts are in the machine. I'm going to do some videos. I'm waiting to get a new camera on how to get in diagnostics and how to use the diagnostics for all these machines, and I'm going to put this up in the members area as I do it. But if anybody has any questions, I pretty much covered over the majority of the parts. I didn't go over the actual troubleshooting of it. I went over more of like what each part was and some of the testing procedures. I'm going to make a video and go through the LG washer in my shop, and I'll go through testing every single one of them, and I'll post that side by side with this video, where I'll actually add the like, say, okay, if you're going to check for voltage on this lamp, this is how you do it and this is where you do it. But I'm going to do it on my GE washer, not my LG. Does anybody have any questions? Because we're running across the 1 o'clock hour.